Sir, Sinu sir, you can start.
Okay, sir. So welcome back all the participants. In the morning session, we have seen design based on ASMD concept. So we have designed a frame energy computation module, and I think we have completed the entire design. And I hope all the participants have also completed design from their end. If you are not able to follow me while at the time of coding, then I have shared the .v file of the design, that is frame energy.v. Uh, if you have completed, no issues. If you have not completed, then just try to take that copy. And now we will proceed with the writing the test bench for this file, and check how our module is working. So before that, let me present my screen. I hope my screen is visible to everyone. Yeah. Yes. So this is a module I have been talking about. We have designed it using ASMD design concept. So we have present state logic, next state logic. So present state logic is in the sense sequential state register logic. Next state logic is nothing but a combination of next state logic, and finally you have the output logic. Uh, so for this, how to write a test bench? I already have a test bench file. I will just show it to you. Yes, I think you know how to write a test bench, right? So you
Yes,
want I think you know how to write a test bench, right? So you
yes,
want I think you know how to write a test bench, right? So you
yes,
want I think you know how to write a test bench, right? So you
yes,
want I think you know how to write a test bench, right? So you
yes,
want I think you know how to write a test bench, right? Torrents, you will do one thing. I will just explain you how to write a test bench file. So create a new test bench file, that is frame energy. You please create in Vivado. So for the sake of convenience, I'm just doing it in Notepad file. So as we have seen earlier, so the test bench file we are going to give frame energy. So it's so parenthesis semicolon and X. So how the syntax for the test bench goes? So first you need to define inputs of your test bench. Next you initiate the design under test, that is our module. Next, what you have to do, you have to define you have to generate the clock signal. Finally, you have to give the. So this is a template for writing a test bench. So please follow this notation. I have given just comments. So try to fill. So if this is a template, then how you will be filling the template of the test bench. So first go to your module. In the module you have a set of inputs, right? So copy all those inputs from your design file and just paste it over here. And in the test bench I said, right, all the inputs must be of reg data type. So change this keyword input to reg, and everything should be terminated with a semicolon. So next, what is the outputs of our test bench? So outputs from our module, the test bench, all outputs must be of y. So test bench inputs and outputs are defined. Now instantiate our design under test. So we are pretty much interested to test our frame energy module. So just to instantiate the module, just copy the module name followed by the entire port list. So after the module name, you have to use the instance name, can be anything, but here I am using DUT. DUT stands for design under test. So this input key and output keywords are irrelevant, so you can remove them. And finally, this bus width representation is also, you can finally what you can do, just and I said for instantiation you need to put it then parenthesis after the port name. So I am repeating all these steps means in order to make you test benches on your own. So in case if you have missed earlier demonstration, so this is complete. Now what we have to do, test bench inputs should be connected to module inputs. So for simplicity, what I did is module input name, output. So going on top, you can just copy and paste. So like this. So this is frame energy module. In that it has a clock input. So to the clock input, we are connecting the clock input of our test bench. So that is me. So this is called port mapping. Next, we need to write initial conditions. So for this, we will be using the initial procedure, begin and end, and these initial conditions only we will write for the test bench inputs. So test bench inputs. And give the initial values of all the test bench inputs. So Next, to generate a clock signal, we are using all simulation purpose. So the clock is 10 nanoseconds clock, so having a half period of 5 nanoseconds. So for every 5 nanoseconds, the clock signal should follow. So initially the clock is 0. After 5 nanoseconds delay, the clock will be 1. Again after 5 nanoseconds delay, clock will be 0. So on and so forth. The process repeats continuously. We have to write the test. So whenever you are writing a test bench, the first criteria. So in our case, if you look into the design, we have used active low reset. So make sure to give active low reset. So I have seen so many people, they will give active low reset, but in the test bench they will give active high, and they will keep on telling like this is to be aware of. So here active low reset. So that is the reason. First I am resetting it for with using 0 active low. After that I am releasing the reset signal. So after that what we have to do? Next we need to provide the start signal. No, before providing the start signal we have to tell what is our frame size. So in order to calculate the energy, we need to tell how many samples it needs to accumulate and treat it as a single frame, and then it has to give the frame, it has to give the frame energy. So since if you can see here on top, the frame size is 10 down to 0, that is 11 bits. So we are representing, we have chosen a frame size of 8 for this example. So 11 take decimal 8. So 11 bits of decimal 8. So that is a frame size. This frame size I am giving after a delay of 10 nanoseconds from when the reset signal is removed. So once the frame size is set, we can directly give a start signal. So start equal to, after that you can remove the start signal. So once you give it the start signal, in the module you can definition you can see ideally it is in the S0 state. Once if you give the start signal, what it will do, it will directly jump into the S1 state, and in the S1 state all these operations will work only when frame sample valid is logic high. Otherwise it won't do any operation, it will just wait in the S1 state. So in the test bench you can see we make start equal to 1 and start equal to 0. Now the test bench is in the S1 state and it is waiting for the sample. So what we do is first we make a frame sample valid equal to 1. Valid equal to 1, and immediately what we do, we give some frame sample value. So in this test bench, what I'm doing is I'm manually feeding the values for your initial understanding. Later we will see how to load these values from a text file. So first we will see how to, first we'll verify the functionality like a preliminary step. So you made a frame valid to be 1, and in this case what we are assuming is we are giving the sample, each sample on every clock edge. That's why we are making frame valid to be high for only one time, and then in each and every clock cycle where we try to do new sample to the, so again with a delay of 10 nanoseconds we will do the second sample. So first sample, this is the binary equivalent and a decimal value is 0.5, and second minus 0.25. So I will tell how I got these values. So similarly, what I did is I have taken up to 8 sample values. Um, okay, I think you need all these values, right? Uh, can you please confirm whether you people are having MATLAB in your systems? Because in order to generate these values, I will tell you how to generate from MATLAB. Okay, okay, don't have MATLAB. Okay, then I will do one thing. How can I share all these values for two students? Can you please let me know in the
Sir,
chat?
Srinu, sir,
Sir.
you share to me, I will forward it to the participants. Sir.
Okay, sir. Okay, better I will share the entire file. So just look at it. So total you can see 8 samples are there. Sample 1, 2, 3, 4, 5, 6, 7, 8. After the 8 sample has been sent, what we are doing, frame valid, we are making it to 0. So this is how the test bench looks like. Let me share this file to you people. Yeah, I have shared it to Dr. M. Mahesh, sir. So you can please. Okay. You can please take that file. Uh, by the time all the students get their copy of this file in their Vivara project, I will just, for the example purpose, I will just tell how to generate all these values through Matlab. There's a small script, I think. In the meantime, participants just copy that file in your folder, in your directory. So I'm opening a Matlab script file uh, that I have written to convert the values into fixed point quantity. Yeah, 0.5. Okay, so I have taken a sample data. The As I told you in the morning, the data is in the range of -1 to +1. So I have taken the data in such a way that it has some positive and negative values. So the data samples are as follows: 0 0.5, 0 minus 0.25, 0, minus 0.0625, 0.0625, 0, 0.25, and minus 0.25. I think the font size is smaller. Let me try to increase it. I think this is somewhat clear as of now. Okay. So this is a variable. Just a minute. Okay, this is the first. I have taken in this script. I have kept two frame data, but in the test bench I used only one frame, so no problem. So first, what I'm doing is, so I'm running this command. So I have generated 8 values, 8 samples. So these 8 samples, I'm considering it to be as one frame. So if you want to calculate the frame energy, what you have to do, you have to do square of each sample and do a running sum. So that is the code for this is the code for in Matlab. So if you do, the energy value is 0.4453. Now in the simulation, we'll check whether we are able to get this value from the hardware module or not. So, but first of all, we need to feed all these frame samples in fixed point binary, right? So in MATLAB, there is a object called signed fixed point object. This is a function called SFI. Inside the SFI, you have a syntax as follows. First, you have to give the variable name which has the data. In our case, the variable name is FP1, which has the frame sample data. So this FP1, what I'm doing is I'm trying to convert into signed fixed point binary, wherein the word size is 16 and the fractional length is 14. That means integer part length is 2 bits. So this is an object. So first let me run that object. So fixed point object has been generated. Now what we have to do is you have to pass this object inside a function called binary function bin in order to get the binary sequence. So if you do so, you will be getting the binary. So these are the values that I loaded in the test bench. So you can see. So in this way, you can convert the floating point number in MATLAB into signed fixed point representation, and that signed fixed point representation you can finally convert into binary bit stream. That values you can put it in. You just copy and you can do it. You can paste it in your test bench. So this is how it goes like. Even if you are familiar with Python, you can do the similar kind of stuff. So since I'm familiar with MATLAB, I have done it in this way. So this I will minimize it. You can see the energy value that the MATLAB is giving it to be as 0.5. Now what we do is we will check whether we are able to get the same value in our test bench or not. So I hope everyone has copied the test bench file that I have given. And once you have placed it in your directory, you make sure that in your design folder, frame energy is set as top, and subsequently the frame energy TB in the simulation folder is set as top. And if you expand that under the test bench file, you should have the DUT file, that is design under test file. So once this hierarchy has been achieved, you can click on run simulation and click on run behavioral simulation. So now the simulation window will open. Everyone try to open the simulation window along with me. Why? Because you have to do few settings in the simulation environment in order to visualize the output. So I hope everyone has able to get a similar kind of a simulation. So what you can do is come to the 0 nanosecond timestamp. Just zoom it, and on the left hand side you can see the signals. If you are unable to see the signals, what you can do is on the left hand side there is a scope available. In this scope you select your test bench file. Once you select the test bench file, on the right hand side it will list all the objects. So all the top level objects in the test bench will be listed. You will select everything, right click on it and click on add to waveform. After adding to waveform, you can click on this anti-clockwise circle diagram, that is relaunch simulation. Then you will be getting the timing waveform. In case if you are not getting any waveform, you can do this procedure. Once after doing that, what you have to do initial settings is first clock is fine, reset is fine, start is fine. Frame size, actually it is a binary number, so that you can right click on it, click on radix, and you can click on unsigned decimal. So we have given a frame size of 8. So for every 8 samples, the energy value needs to be computed. Next, we have a data bus called frame sample input, that is 15 down to 0, 16 bits. By default, it will be in hexadecimal format. So but in our case, it is a real number represented in signed fixed point binary, wherein the 16 bits is equal to signed fixed point binary having 2 bits reserved for integer part and 14 bits reserved for fractional part, wherein the 2 bits in integer part, the MSB bit is the sign bit and the LSB bit is the magnitude bit. So you just right click on the frame sample, go to the radix. Earlier we have used the radix called binary, hexadecimal, octal, unsigned decimal, like that. But now this is a real number. So what you have to do is you have to click on real settings. Once you click on real settings, it is asking you whether how to represent this binary sequence in a fixed point binary or a floating point binary. So ours is a fixed point representation. So you select fixed point. After selecting the fixed point, it is asking you whether it is a signed fixed point or an unsigned fixed point. So in our case, the frame sample input is a signed fixed point. So you please select signed fixed point. And now it is asking you where to place the decimal point. So at which location? So if you see, ours is a 16 bit, in the 2 bits are reserved for integer part. So that means 15th and 14th bit are the integer part. Right from 13 down to 0, that is those 14 bits are the fractional part. That means the decimal point should come after the 14th bit. After the 14th bit. So that's why here I'm saying place the decimal point after the 14th bit. And now you click on apply and OK. Now you can see our frame sample values in the decimal format. I mean the real number format. So you can see here our first sample is 0.5, second sample minus 0.25, third sample is 0, fourth sample is minus 0.0625, fifth sample is 0.0625, sixth sample is 0, seventh sample is 0.25, and eighth sample is minus 0.25. Similarly, the energy, that is 24 down to 0, that is a 25 bit bus. You right click on it, click on radix. Again, this is also a real number. So click on real settings. If you click on real settings, again, it will be asking you, since it is a fixed point, select fixed point. And energy value is unsigned. It is unsigned fixed point. Why? Because energy value is always positive. So there is no chance of getting a negative energy. That's why what we have done is we have chosen unsigned fixed point. And similarly, where to place the decimal point? So it should be placed after the 14th bit. So you click on apply and click on OK. Actually, this decimal point, it is calculating from the LSB side, LSB to MSB. So after the 14th point, why? Because in energy, first 14 bits are the fractional part. After that, we have 11 bits. 11 bits are dedicated for the integer part. Why we have dedicated 11 bits in integer part means the frame size we have considered maximum to be 1024. And for suppose, if we take all the frame samples to be a maximum value of 1, sum of all ones up to 1024 samples is value 1024. To represent 1024, we require at least 11 bits in the integer part. That is the reason we took 11 bits in the integer part. And since this is a real number, in order to represent the fractional part, we took 14 bits at the fractional part. So 14 plus 11, it is 25. So now you can observe here. So once first we kept a reset to be active low. So module has been reset. So how do you know module has been reset or not? In that module, we have an energy register, right? that register is directly connected to the energy output. So immediately once you started the waveform, the energy is having an unknown value. So on arrival of a positive blockage and on application of a reset signal, the reset has been activated and the energy register is reset to 0. That's why the value you can see from red to it has generated color has changed to black in my case. I think in your case it should be red to green. So energy value, energy register is set to 0. That's why energy output is coming to be 0. After some time we release it to reset, and after that we have given the frame size to be 8. After some time what we have done, we have initiated the start signal. So once we have initiated the start signal, the actually what it has happened means in the next clock cycle, FSM has switched from S0 to S1. Whether really FSM has switched or not, how we will know? You have to add the signals of FSM over here, so that I will tell you. So first right click on it and click on add a divider. So iOS, this divider you can place it at top. Only to distinguish between the waveforms you can add a divider. So next divider I'm adding. So on the left hand side there is a scope available, right? So there by default test bench is selected. Now you select DUT. Once you select DUT, all the DUT inputs, outputs and internal signals and registers will be listed out, all the objects. So in that what you do is add the state registers, that is a register, state register logic and state register combinational next state logic, that is state reg and state next. And you'll just relaunch this simulation. Here you can see how the states are being switched. So by default the ASMD, the FS is in the S0 state. So S0 means represented with the state 0. So whenever you are giving a start signal, combinational next state logic has updated whenever its logic start like signal. Next state should be combinational S1. Next state logic that is indicated has updated whenever your logic start signal. Next state should on be combinational next state logic has updated whenever your logic start signal. Next state that is on combinational next state logic has updated whenever your logic start logic that is on combinational next state logic has updated on logic start logic that is on combinational next state logic has updated. So once it is set to the S1 state, what it will do? First, it has to wait for the frame valid, frame sample valid signal. So here you can see at this instant, the frame sample valid is 0. So since it is 0, it indicates that there is no valid sample that is coming to the input of the module. So what the FSM will do, it will wait in the S1 state and it will not do any operation. In the next clock edge, again there is no frame sample valid is coming, but at the negative clock edge we got a frame sample valid to be high. When you are getting this frame sample valid to be high, what the combinational next state logic will do, it gets activated, and what it will do, it will read the data line, that is frame sample, and first what it will do, it will do the squaring operation and it will calculate the value. So that how that square value where it is present in our module, if you check here in the code, the square value is given by the prod. It is a reg data type prod. So that prod that you need to just add to the waveform in order to just visualize it. We are at the 60 nanoseconds timestamp. Remember, I'm just relaunching the waveform. So we are at the 60 nanoseconds timestamp. can see the product is actually 16-bit into 16-bit. Actually, the resultant is 32-bit. So if you, this is in the hexadecimal format, we will change it into binary signed fixed point format. Signed, because two are signed numbers, right? The resultant is also signed. And the binary point 14 plus 14, 28. It should be at 28th position. And you can see we got 0.25. So when you are getting at a negative clock edge, we gave the frame sample value to be logic high. So since it is a combinational logic, irrespective of the clock, what it will do, it will calculate. So 0.5 into 0.5, it is 0.25. On arrival of a positive clock edge, what it will happen, this 0.25 value will directly go into the energy register. See how in the module how we have written. So first what it is doing, first we have to do product. After that we are doing part selection, and that we are adding it to the already existing value in the energy register. Currently in the energy register the value is 0. Let me add that energy register also. Where is that energy register? Energy underscore reg. Just let me add. Relaunch the waveform. So this is 24-bit, right? So can we change it to, yeah. Forget about the next state logic, it keeps on fluctuating, but only take into consideration of the register value. So earlier when you give the value 0.5, the product value is computed as 0.25, and the energy next value is calculated as product plus current value. So current value in the register is 0, product value is 0.25. So ultimately the end value is 0.25. This computed value will be updated in the register on the next arrival clock edge over here. So soon after, again what happened, you gave a new sample that is minus 0.25. So square of 0.25 is 0.0625. This value now it is added to the existing value 0.25 in the register. That becomes 0.3125. So on and so forth. This process will proceed till the count value. We also have a counter, right? That what is the counter name? That counter name is sample count underscore reg. So from the external input, we are telling like the frame size should be 8. So internally, what we are doing, internally we are running one counter. So that counter name is sample underscore count. That I will add it to the waveform again, and I will relaunch the simulation. And once that sample count, the counter value is reaching 7, that is the maximum count, it indicates that 8 samples has been processed and energy value has been computed. You can see here when the count register value is becoming 7, at that time what happened is when it is in the 7th sample, so it has already received the 7th sample, that is last sample minus 0.25. For that it has already calculated the product value, that is 0.0625, and energy value is also computed, that is 0.4453, and this value will be updated in the next arrival clock edge. But however, at this instant, since the count value has already reached to the maximum value, that is 7, what had happened is the next state it has calculated to be 0. Why? Because all the 8 samples has been processed successfully as of now. So on arrival of the clock edge, what it is going to do, it is going to jump to the S0 state. So you can see it has collected the 70 sample, it has squared it, and it has added. In the next state logic, it has updated, like it has to, the value has been updated. And on arrival of a clock edge, what happened? The energy register holds the final value. The FSM has switched to the S0 state, and accordingly, energy valid is made to be active high, indicating that whatever the value that is coming on the energy output is a valid energy output. And you can see further the frame valid, frame sample valid is made 0 in that same clock cycle to the input of the module. We are saying like all the samples, the signal has been processed and there is no further any signal. So in the subsequent clock cycle, the frame energy value should become active low. So for that reason only, at the end, I told you I am writing this condition like whenever the FSM switches from S0 to S1 state, at that time energy valid will be active high, so that it should not remain active high for all the time. That's why I have written this condition, energy valid next should be low. So what that will do is it will pull down the energy valid output to logic 0 after one clock cycle. And since the frame start signal is also at a low, why? Because the transition from S0 to S1 is controlled by start. It is governed by the start signal, right? Since the start signal is low, there is no further any signal coming to the module. And after this clock cycle, the FSM continuously remains in the S0 state. That is defined by the state bridge. So no further state transition is happening, and FSM is remaining in the S0 state, and now it is in the idle mode. When it is in the idle mode, the ready should be at logic high. So soon after FSM enters into the S0 state, the ready output is made logic high. So while it is in computation phase, that is S1 state, the ready output is logic low, that you can see over here. So this is how we have designed our module. And in the morning, I have just given some specifications. After the specifications, we have started designing our module. Now we have written the test bench and we have simulated it. And from the simulation, we can justify that whatever the design specifications that we have discussed earlier, everything is matched by our module. So simulation, it is working fine. But next, we need to ensure whether our RTL is in a proper format or not, and from this RTL description, whatever we have written, whether are we able to realize a circuit out of it or not. So that how you will know functionally. Now our script, our RTL HDL description, functionally it is valid, but we need to check at the same time whether we are able to realize a valid circuit out of it. That means whether we are able to synthesize your HDL. HDL description, whether you are able to synthesize and you are able to get equivalent RTL or a gate level netlist or not, that you have to check. That how you will check, you have to run synthesis. So once you run the synthesis, if you don't have any errors or warnings, that is an indication like your entire HDL description, whatever you have written for this module, has been equivalently transformed into the RTL or a gate level netlist. So in order to open the RTL schematic, you can just click on the schematic under the RTL analysis, and it will open you the elaborated RTL or gate level netlist. So it is taking a little bit time. So this is a schematic of our design. earlier you can see like for small designs the schematic is very just enough. So as the level of complexity increases, the netlist also becomes very much complicated. This is your actual entire circuit in gate level netlist. So you can just zoom in and you can just go through all the elements. So on the left hand side here you can see the inputs. So you have some muxes, you have some adders, you have some registers, here you have some subtractor, and if you just go like this you can see, and here you have a multiplier, and you can see here we have three outputs, right? So all the outputs are driven from a register. So this is a register driven by the driving the output. This is a flip-flop driving a single bit output. Again, this is also a flip-flop driving the single bit output. Similarly, after synthesis, what you can do, you can also see the synthesizer netlist in terms of FPGA. So for that, you can click on synthesis and you can click on schematic. Now you will get the description that is transformed into equivalent FPGA netlist. So in FPGA, we have basic building blocks like CLBs. Inside CLBs, we'll have lookup tables. So now your entire architecture is represented in the form of a FPGA netlist. So this is how it looks like. You can just zoom in and you can check. So you can see lookup tables are there here and there. Some input buffers. And main thing is, this is the one I was discussing about. This is the DSP48E slice. This is a dedicated resource available on latest FPGA fabric inside the FPGA. Along with the configurable logic blocks, you will have DSP processor block, where these are the specialized blocks which are used to perform arithmetic operations, mainly the multiplier. So in our case, we are squaring the sample values, right? So for that squaring, this one DSP block is used to realize a multiplier. And everything is represented in terms of FPGA resources. It is very difficult to understand how these are interconnected, where is our signal and all. So I'm just showing it for your understanding purpose. So don't try to interpret these diagrams and this thing, because you cannot find your whatever the names you have given. It will add its own naming syntaxes for to derive several different components of a common signal, and it will represent in this format. So for a very complicated design, it will be very difficult for us to interpret and understand. So this is generated by the tool. So in this way your netlist looks like. So that's it. This one, as of now, I think we can run implementation, but we cannot run the bitstream. Why? Because we cannot implement it directly as of now. Why? Because so here you can see we have very big data buses, inputs and outputs. And also I told you in the simulation we have seen, right? For each and every clock cycle, we gave a new sample. So by using the GPIO pins and all, we cannot give all these inputs. If you want to really test this on the FPGA, by putting it on the FPGA and check, we need to design one more circuit that is called a data source circuit. That is also again based on the FSM concept, and in that we have to create one small memory, and in that memory we have to store the data, and we have to run that FSM in such a way like it will read each sample from the memory and output that sample on an output line, wherein that output line is connected directly to this frame sample input. In that case, we can create some configuration and try to integrate the data source with the frame energy. That entire module combinedly you can put it on FPGA by configuring it with ILA cores and VIO IP cores that we have seen yesterday. And in the ILA IP core, you can give the trigger and then you can observe the output. That I will show you how to do it. But as of now, this design as it is, we cannot put it on FPGA. We need some interface logic in order to run this design on the board. So as of now, you can do up to simulation and you can check the outputs. And then what you can do is in the test bench, you can try to change these values. But when you are changing these values, just check, compute the energy value manually or else in the Matlab or any Python or a C language as per your convenience, and run. And then what you do is run the simulation and check whether the outputs are getting matched or not. So in this way, we will do the functional verification. You can run the synthesis process and check whether or if you are getting any errors or warnings. If there are any, I will just assist you in clearing all those things. So that's it from my side as of now. We can take a small break. If any participants are having any issue, I will try to address them. Yeah, anyone please communicate with me. What is the current status? Hello. Sir, what is the status, sir? Whether all the participants has completed the simulation along with me?
Sir, Srinu, sir.
Sir.
Actually, the students are actually really lagging. They are behind because, however, we have made this YouTube live streaming. They are
Okay,
slowly
sir.
working with it. I think by today night they will complete, sir. You can continue as per the schedule because nothing can be skipped. If any doubts persist further, also we can communicate with you.
Okay, sir. So you want me to proceed? Okay.
No, no, you take a break for 5 minutes.
Okay, okay, sir. So
So that
after
if you
that,
continue, the students
you
will.
want me to go to the next concept?
Yes, yes, yes.
Okay, okay.
Okay.
So I'll be back in a while. In the meantime, participants try to complete the simulation till here. After that, we shall continue.
Sir, students are following the YouTube live stream.
Sir, your voice is breaking.
Okay, I will call you, sir. I will call you.
Okay, okay, sir. Yeah, welcome back all. We shall continue our session. Uh, let me present my screen first. Yeah. So I hope participants have simulated it perfectly. Even if you have not simulated and if you are still going on, so not an issue. Try to complete it at the end of the day. Mm. Just pay some attention. I will be discussing a few important topics as well. So, in the test bench, if you look into the test bench, you can see we have manually fed the values in the test bench like this. So, for a frame size of 8 samples, say for example, if we have a frame size that we are dealing with, maybe 256 samples or 128 or a 512 or a 1024, it is always a cumbersome process to type all these frame sample equal to and a value. The code becomes very ugly. Why? Because we'll have a lot of lines. It's not modular in structure, and also at the same time it is also difficult to write sample by sample in this fashion. So earlier I told like we will be using file IO operations, wherein we take the data from a text file, and then load it into the test bench, and read sample by sample from that file, give it to the module, test the module, and what are the outputs we are getting from the module, that again we will dump into another text file. So we have a data in.txt file and data out.txt file. So in yesterday's example, I have covered like how to you dump the outputs of a module into a text file. And that in that example, we since we use deal with counter based examples, so to counter we are not giving any input, only the count value whatever we are getting, that we try to dump it into a text file, and then we have visualized how the outputs are being dumped into a text file. So now in this example, what you can do, this is a very perfectly good example where you have the inputs. So these inputs, instead of giving them manually in the test bench, you can give it from a text file itself. From the text file, you can just read the data, and you can just pass it to the module, and the module outputs you can capture it and you can dump it into the another text file. So the dumping part of capturing the outputs and dumping it to the text file, that I won't discuss as of now. Why? Because that anyhow we have covered yesterday. How to import the data from the text file and give it to the module, that we will cover in this example. Later on, as a kind of a homework kind of thing, what you can do for this frame energy module itself, you can write a test bench with having reading the data from a text file, and then dumping the outputs of the module from the simulation window to the text file. You can combine yesterday's example as well as today's example that I'm going to deal now, and try to write a test bench with two text files, data in.txt to read the data from the file and test the module, and data out.txt file wherein you will be dumping the desired outputs obtained but from your module, so that you can take it as a homework task. So without wasting further time, let's check how we can modify this existing test bench. So I won't be directly modifying the test bench. So I just want to preserve a copy. So for that purpose, what I do is I will create a new test bench file. So frame energy underscore TB from a view TB2. Why? Because already frame energy underscore TB is available. So this is again a simulation source. Yeah, it has been added successfully. So this is the file. So I will edit directly from this already the file that I have in Notepad, that I will edit directly. So this time what we are going to do is, so this time the module frame we have inputs will remain the same, outputs will remain the same, so we are not touching it. Instantiation of DUT remains the same, initial conditions remains the same, generation of clock signal remains the same. Only thing is we need to make few modifications. In those modifications, what we have to do is the test stimuli after the initialization process. We want to get rid of entering all this manually, right? So these all things. Scratch itself, right? Because any so these are the mandatory things. These should be pressed on the next. So the very first thing what we need to do is let me use one file. So you have a test bench environment like this, and inside the test bench environment you have a module sitting like this. So now what you are going to do is you know that your test bench has some set of inputs and set of outputs. Test bench inputs are connected to module inputs and module outputs are connected to test bench outputs. So earlier what we did, we kept a file, and what we did, we tried to dump the outputs into a text file. Now at the input side, now we have a test bench file, sorry, text file. This is data out.txt and this is data in.txt. So from this text file we need to load the data. So how this will happen means, first we need to have a data in.txt file. So we assume that we have a file. Next we have to open that file. For that we will be using fopen. Next what we have to do is, inside the test bench we need to create a register file. Why register file? In the sense, I already mentioned you earlier, all the inputs in a test bench should be of reg data type. So this is a text file. So from this text file what you have to do, you have to read all the data samples, and those all data samples you have to store it in a reg data type based memory unit. So this is called as a memory unit. So this is not the actual hardware memory that I am speaking about. So this is for the simulation environment. This memory is different. As you noted, the simulation test benches you cannot realize any hardware. So just assume that it's a kind of a memory unit. So that memory unit has a special name that we call it as a register file. So we need to load the data in the register file in this manner. And next we need to have an index that is maybe treated as an address pointer to the register file. So it will point to the particular address location. Why this index is very what is the significance? Because we need to read sample by sample from the register file, and that sample, what we have to do, we have to put it on this line. So the data needs to we need to place it on this line input, so that this data goes to the module, that is DUT. This is test bench. So this is a basic mechanism that we are going to do. So after declaration of test bench inputs and after declaration of the test bench outputs, so how do you declare a test bench register file? So by default, this is also a reg data type. So if you observe clearly, word file. So earlier what we have done is we always create a reg data type, and then what we did, we gave some variable name, right? Variable name. So this is like one dimensional. So this is a single bit reg. In another case, reg 3 down to 0, and we have given some name, that is a variable name. This is a reg data type of having a width of 4 bits. So now what we have to do is we have to create a register file. So a register file, it is a 2D structure. So it has some rows and it has some columns. So row refers to a unique sample, and column refers bit position. So now we need to, and our interest is to store the frame samples or the signal samples in text file, and from that we need to read each and every sample and give it to the module. So our samples all are 16 bit wide. So like that, how many samples are there? Say for example, in our current example, we have taken a frame size to be 8. That means we need to store at least 8 samples and we need to sample it. So if you look at the structure of a register file, so it should have 8 rows, wherein in each row we can place one sample, and it has 16 columns, wherein each column one bit of data is allocated. So if we take width into depth, so the word size is 16 and the depth is 8. So in this case, what you have to do is how to declare this type of a register file. So again, this is a reg type, reg. You are declaring it as each sample is having a word size of 16 bits, that is 15 down to 0. And for the test bench register file, you may give any generic name. So I am giving tbrf, that is test bench register file. So again, opening brace 0 up to 7. So whatever, this is a variable name, right? So whatever coming to the left hand side, that is treated as word size. Whatever coming to the right hand side, that is treated as the depth size of the register files. So this is a notation that we will generally follow in order to create a memory, not only for the test bench case, even in the design module, we will often, in some designs, we will try to develop modules for RAM and ROM kind of memory units. Again, in RAM, we have a variance, single port or a dual port. Again, in ROM also, we'll have a single port ROM or a dual port ROM, so on and so forth. So for all these cases, whenever you are declaring a memory, we will follow this notation. So this is a syntax that is being followed in Verilog in order to deal with the declaration of memory elements or memory variables. So what we do is I declare a test bench register file. And in this test bench register file, what is the word size? My word size is 16 bits. The name of the register file is test bench register file tbrf. Seven. So this is a test bench register file. So first test, and to access this test bench register file mechanism, what we need to do is we have to create some test bench variables, creating a few number of variables. Tell you what is the significance of each and every variable. These variables by default are in data type. So first, the first variable is index. We use maybe you can use it as like a address variable to fetch the data from a particular location of a test bench register file. And we also require file, and that file will be addressed with respect to a file pointer. So that's why a file pointer variable is also created. So next what we have to do is so in the initial begin end, we have different initial conditions. This is a clock signal. Loading should happen only one time. That's why we are only using initial block. So initial and syntax command for loading the data into a test bench register. Read mem indicates like is a keyword, reserved keyword in to read text file and store it into a test bench register file. So that is $read mem, and how it is supposed to read, whether it has to read the binary data or the hexadecimal data or octal data, what kind of a data. So it is like in our case it is a binary data, That's why we have to use the function called $read_mem_b. So if it is hexadecimal, $read_mem_hex. If it is octal, it is $read_mem_o. So we will use the $read_mem_b, and in the parentheses, what we have to do is to provide the file path, and next we have to tell after reading that file where it needs to store the data. So to store the data, where we need to store, we need to store the data. Okay, correct. Just a minute, I think we don't require file pointer. This readmem itself will it's a straight away function. We need not open any file. By using this function, it will automatically open in the blue page. So okay, so again the syntax remains the same. File name. So what is the file name? It is, and you can also provide the path of the file name. So where I will store that file. So in my main project directory, under sources, under simulation, under new, I want to store the file over here. So I will just copy this path, and what I will do is I will just paste it. And so this is sufficient. So it will load the data into the text expense register file. So once the loading is over, now what we needs to do is we need to read the data from the test expense register file and give it to the model. So for that purpose, how to do the test terminal. What we have to do is makes a transition into its own state. Now, what we have done earlier, we have given sample by sample. For each sample, we have written a single line of code, right? So in this case, that is not necessary. So what we do is we will be using a for loop. For so how the for loop control variable will be in. what is the depth of the test bench register file? The depth of the test bench register file is total depth is 8, varying from 0 to 7. So since index is starting from 0, that index should be so less than or equal to 7, and index so what it is doing, frame sample valid became high. What we are doing is in the test bench register file we have the data placed in the rows. So we are giving the index value to access each sample, and that accessed sample value is fed on to the frame sample input. So soon after sampling it, what it has to do, after that again the process should repeat. So once it exits the loop, what it has sample valid. So this is the case. So I think it is done. So let me check what is previous test bench. So on the previous test bench, yeah, the last command is 0. So only thing, if you see here, in the test simuli, so till the reset frame size start and frame valid is preserved. Again, frame sample valid is made 0. Whatever the things in between are these lines that we have replaced with this for loop. That's it. Now what we can do is we can just I will just copy. Yes, so so there are no syntax errors. Okay, fine. Now only thing is I need to have this data in .txt file. So how to get that? You can use any of the scientific programming language to get that. So here I'm using Matlab. Yeah. So what I do is earlier I have taken frame 1, right? Now values we will take frame 2. I think that is quite different from frame 1. Yeah. Now we run this and we just calculate the energy value for this. Earlier energy value I think for but also we'll check those. And previous frame energy is 0.4453. New frame value is 0.5253. Second frame. So we will use the anyhow we used in the first test bench first frame data. Now we will use second frame data in the second test bench. So the energy values are quite different for both the frames. So we will see whether we are able to get this. So what I do, I just take a new frame. Now for this I calculate the energy. Now what I do, I create a fixed point binary object data, and then I convert the floating point values into signed fixed point binary. So this is the data. Now what I do is you can see here some quotations are there representing a character string, but I don't want these quotations. To remove that, there's a data format change in Matlab. So character data type, table data type. So in table I have this data. So what I do is I copy this data, and what I do, I go to this path. So in this path I want to put a file called data in .text, right? So this is the path. So what I do here, I will create a new text file. In this text file, so I'm good to go. I will click on run simulation and click on run behavioral simulation. So if you remember earlier, I have saved the waveform configuration file for a test bench 1. So it will try to fetch that file and it will open that waveform configuration. And this time in that waveform configuration, all the waveforms are not available. But if you open this waveform configuration file with the first test bench, you can see the timing waveforms with the pre-saved or settings. If you try to launch the simulation in the old waveform configuration file, then whatever the settings that you made with respect to your first test bench, everything will go. So that's why what I will do is I will close this and I will go click on file. I will click on simulation waveform and I will click on new configuration. So a new waveform configuration window has been generated for this second test bench file. So this I save it as test bench 2 waveform configuration file. The name goes as follows: frame energy underscore tb2 underscore behavioral dot wcfg. So this I save it. Now what I do is I add the test bench objects. So test bench inputs and outputs. So clock, reset, start, frame size, frame sample, frame G energy valid, ready. These are the actual test bench objects connected to the inputs and outputs of our actual module. So here I'll add a new divider. And at the bottom you can see test bench register file, tbrf and index. These are purely related to the test bench variables. They have no significance with respect to the actual module. So now what I do, I will just run the simulation. I will relaunch the simulation. So the simulation is complete. So I will, you can see everything is in hexadecimal. So step by step I will change it into real number radix. So clock is fine, reset is fine, start is fine. Frame size, it is in hexadecimal, but it should be in unsigned decimal. I will change it. So you can see the frame size, what we said, it is 8. Frame sample, it is a real number, but it is in hexadecimal. So the real number, I will change the radix. Click on fixed point. Frame sample is a signed, so signed, and binary point is at the 14th bit. So apply and OK. So you can see the values. This time new set of values, that is for frame 2, 0.5 minus 0.25, 0.2, minus 0.0625, 0.0625 minus 0.2, 0.25 minus 0.2. Earlier we used two zeros. The two zeros we replaced with 0.4. Now the energy value, that is also an hexadecimal, but we want it to be in real value. So it is energy is unsigned and present after 14th bit. So okay. Next test bench objects, you can see we have the depth is 8. So having address from 0. This is a memory file which consists of the data of a signal that is loaded from a text file, that is data in .txt. So that data is loaded successfully in our test bench register file that you can see, and this is the index. This index is used to run the for loop and also to serves as a addressing index for to fetch the data from the test bench register file. So you can see each and every sample is being read from the test bench register file, and that sample is fed on to the frame sample input of the test bench, and through the test bench input it is reaching our frame sample input of our module. And finally, after all the 8 samples, the energy value is computed to be 0.525268. From the Matlab, we get the value to be 0.5253. So more or less we got the same value. So what is the error? 0. Actual value is this P2, right? Minus what is the value given by our module? 0.5. And the error is 4.39 into 10 to the power minus 5. This small significant error is due to the truncation, since we have truncated the value to 25 bits. So ultimately, the functionality of our module is once again verified with a new set of test cases. This time the test cases are loaded in the data in .txt file. From the text file we just read the data into our test bench, and then we passed the data to our module and we verified the computed output. The output value, energy value computed by our module is more or less nearly equal to the value given by, that is computed in Matlab for the same test case. So that's it. So the motivation in this exercise is like I just wanted to illustrate you how to use a text file, load it into a test bench and read samples from the text file, and do the simulation. So that's it. I conclude this over here, and if anyone has any doubts they can ask me, or else if you people are still doing it, you can take some time to finish it. We will continue with the next concept after a small break. Okay, sir. If the students want this file, means I will just share it to Mahesh sir, and you people can collect this file, the second test bench file.